When most people think of mathematics, their minds drift toward cryptic equations and the need to solve for x. Here we'll study a very broad class of equations known as Diophantine equations. These equations are such that they only involve integers and for which we only desire integer solutions. They're named in honor of the influential 3rd century Greek mathematician Diophantus of Alexandria. We'll begin with his story and the history of these long-studied important equations. Determining whether a Diophantine equation has solutions or has no solutions, or has finitely many solutions, or infinitely many solutions, actually remains extremely challenging and has become genuinely an art form. Here we'll examine the famous but misnamed Pell equation in order to introduce Fermat's method of ascent, an important technique for finding infinitely many solutions to a Diophantine equation. We'll close this lecture with a brief discussion of a famous meta-question posed by the great German mathematician David Hilbert. In a famous address delivered in Paris to the International Mathematics Congress at the dawn of the 20th century, Hilbert posed 23 open questions that he believed would lead to new important frontiers in mathematical investigation. His 10th question asked if there exists an algorithm for determining whether or not an arbitrary Diophantine equation has an integer solution. As we'll see here, a complete answer to this question was only found in 1970 and remarkably involves the Fibonacci numbers. These algebraic equations open our exploration into algebraic number theory. Well, we open this lecture by introducing Diophantus of Alexandria and his passion for arithmetic. Diophantus of Alexandria was a great mathematician from the 3rd century. Very little is actually known about the life of Diophantus outside of a conundrum that appeared in the Greek anthology from 600 CE. Referring to the life of Diophantus, the puzzle reads, God granted him to be a boy for the 6th part of his life and added a 12th part to this. God clothed his cheeks with down. God lit him the light of wedlock after a 7th part, and 5 years after his marriage, God granted him a son. Alas, late-born wretched child, after attaining the measure of half his father's life, chill fate took him. After consoling his grief by this science of numbers for 4 years, he ended his life. Well, the algebraic riddle was, using this information, how old was Diophantus when he died? If we let x denote his age, then the previous sad puzzle can be translated into the sterile equation, x divided by 6 plus x divided by 12 plus x divided by 7 plus 5 plus x divided by 2 plus 4 equals x. And if we solve this equation, we would find that x equals 84, the age at which Diophantus supposedly died. In fact, this sad story and its solution actually highlight Diophantus's greatest mathematical passion, searching for natural number solutions to certain equations. Diophantus made enormous contributions to algebra, and in fact is often referred to as the father of algebra. For one thing, he's believed to be the first Greek mathematician to actually accept rational numbers as numbers. Up to that point, for example, the Pythagoreans looked at rational numbers as ratios of numbers, but not as God-given numbers themselves. But perhaps more importantly, Diophantus is credited for introducing mathematical notation and symbols for solving equations rather than prose, which was the custom of the time. And imagine, if you will, that equations and mathematical objects of the sort were written actually in words. One would say, imagine some unknown quantity whence multiplied by 18 and then increased by 45 results in an answer of 64. And now you're supposed to find the unknown. Well, if it's literally written out in words, it's a great challenge. And Dauphintus was one of the first to actually record these ideas using symbols and thus led to the advances of algebra. Well, he was particularly interested in finding natural number solutions to certain equations. If a solution turned out to be a fraction, then he would actually accept that reality. However, Dauphintus viewed negative solutions or irrational solutions as useless or meaningless or absurd, perhaps because his equations often arose from counting objects. And it was okay to have half of an object, like that kind of rational number, but -3 objects didn't make sense. In fact, he once called the equation 4x plus 24 equals 4 absurd, because the answer, x equals -5, and we can check that x equals -5 is the answer. If we plug in -5, 4 times -5 is -20, plus 24 equals 4. And -5 is negative. So, I mean, if, for example, that represented how many people? Maybe 4 times a certain number of people plus 24 equals 4. What number of people do we have? Well, -5 people doesn't make sense. So he called these things absurd, which makes a little bit of sense if you think about it. Dauphintus' most important work was a 13-volume collection of books entitled Arithmetica. Unfortunately, only 6 volumes have been found to date. Now, the volumes are perhaps the first algebra text ever written in that algebra questions are posed and the solutions are given using the notation that later evolved into our present mathematical symbolic language. In 1570, the Italian mathematician Raphael Bombelli was the first to translate Dauphintus' books into Latin. And this was an extremely important contribution because it brought Dauphintus' seminal work to a very large audience. In fact, we'll visit Bombelli's 1621 Latin translation of Arithmetica in the next lecture in regards to a wonderful story involving Pierre de Fermat. Today, if we consider an equation and wish to determine if there exist integer solutions, we call the equation a Dauphintine equation in honor of Dauphintus. Thus, given a Dauphintine equation, our implicit goal is to determine if there are integer solutions or not. If there are integer solutions, then the follow-up questions include, are there finitely many or infinitely many solutions, and can we find them all? For example, if we consider the Dauphintine equation 2x plus 1 equals 7, then we can find that there are only finitely many solutions. In fact, there's only one solution, x equals 3. And we can check if we let x equals 3, 2 times 3 is 6, plus 1 is 7, and that's the only solution we have. If we consider the slightly altered equation, 2x plus 1 equals 6, then we find that there are no integer solutions. However, there's exactly one rational solution, x equals 5/2. And again, we can check. If we let x equal 5/2, 5/2 times 2 is 5, plus 1 equals 6. Well, if we consider the equation x squared equals 16, then we see that this equation has only finitely many solutions as well. In fact, just 2 solutions, x equals 4 and x equals -4. And again, if we take either of those answers and square, we do see 16. However, if we consider x squared equals -1, then this equation has no integer solutions, since in fact we would require the imaginary number I, which equals the square root of -1. Finally, we return to an equation that we saw in our earlier lecture on relatively prime integers, and that we just celebrated in the previous lecture on RSA public key cryptography. For relatively prime natural numbers a and b, we considered the equation a times x minus b times y equals 1. Now, in fact, this equation has infinitely many natural number solutions. For example, if we consider 3x minus 2y equals 1, it's easy to see that x equals 1 and y equals 1 forms a solution. Notice 3 times 1 minus 2 times 1 equals, well, 3 minus 2, which is 1. So it's a solution. In fact, so is x equals 3, y equals 4, because if I plug those values in, I would see 9 minus 8, which still yields 1. In fact, so is the solution x equals 5 and y equals 7. 5 times 3 is 15, minus 14 yields again 1. Well, while it's not at all obvious, there's actually a pattern in these solutions, and I want to share them with you. In fact, there are actually two formulas that give us infinitely many solutions to this type of equation. And these formulas can be stated as x equals 2 times n plus 1, and y equals 3 times n plus 1, where n can take on any integer value. Here, in some sense, the n can be viewed as a variable or as a parameter. So we can let n vary where n equals, let's say, 0, 1, 2, and so forth, and then the x and the y will change correspondingly. So, for example, if we take a look at the solutions, if we let n equal 0, then we find the solution x equals 1, y equals 1. If we let n equal 1, then we see again the solution x equals 3, y equals 4. If we let n equal 2, then we see the solution x equals 5, y equals 7, and so on. If we let n equal 3, then we see the solution x equals 7, y equals 10, and so on. Well, this example leads to the most fundamental issue in the area of study: determining if Diophantine equations actually have integer solutions. All the equations we consider here will always be sums, differences, products, and powers of integers and unknowns. So the recurring question is, are there integer solutions to these expressions? Well, if we have an integer solution, then we'd have an equality between two integers. If we found an integer solution, when we plug them in, we'd have an integer equals an integer, namely itself. Well, therefore, the left and right sides of the equation must have equal remainders when divided by any particular natural number. So let's think about this. Well, if we stand this observation on its head, we see the following. If we can find a natural number, let's call it m, so that dividing by m gives a different remainder on the left side as we get on the right side of the equation, then there cannot be integer solutions to the original equation because we have a contradiction. We would have to have the same remainder. So, for example, let's consider the equation 4 times x equals 2 times y cubed plus 1. Now, if we assume that there are integer values for x and y that satisfy the equation, then what if we consider the remainder of each side of this equation when we divide by 2? Well, on the left-hand side, notice we have 4 times x. So no matter what x is, as long as it's a natural number, 4 times x will always be even because it's an even number. So the remainder will always be 0 when we divide that by 2. While on the right-hand side, notice that the 2 times y cubed is even, but when I increase by 1, plus 1, it automatically becomes odd. So its remainder when we divide by 2 will be a 1. In other words, the remainders are not equal, and therefore it is impossible for the two sides of the equation to be equal integers. So there are no integer solutions to this equation. Well, modular arithmetic can be used quite often to show that certain Diophantine equations have no integer solutions at all. One of the most famous Diophantine equations is associated with the all-important Pythagorean theorem involving right triangles from geometry. We'll highlight the Pythagorean theorem, its proof, and its connection with number theory in lecture 16. But for now, we'll just recall its famous equation, x squared plus y squared equals z squared. Well, are there natural number solutions to this equation? The answer is yes. In fact, there's a well-known solution, x equals 3, y equals 4, and z equals 5. And let's check that's a solution. If we square 3, we get 9. If we square 4, we get 16. When we add them up, we get 25, which indeed is 5 squared. Well, are there others? Well, sure. 6, 8, and 10, in fact, also forms a solution, but it really is just the previous solution, 3, 4, 5, doubled. So not very interesting. So the question really is, are there other genuinely different solutions? And the answer still remains yes. For example, let x equal 5, let y equal 12, and z equal 13. And in fact, what we see here is another solution. 5 squared is 25, 12 squared is 144, and when we add them together, we get 169, which notice is indeed 13 squared. Well, these natural number solutions are known as Pythagorean triples. So the question is, are there infinitely many Pythagorean triples? Well, we'll return to this important question in lecture 16. So it'll be a mathematical cliffhanger, if you will. Well, as we've just seen, the Pythagorean equation is one that involves squares, namely powers of 2. We now introduce another collection of famous equations that also involve squares. Another example, a particular example of this type of equation is x squared minus 2 times y squared equals 1. Notice the squares. And more generally, this type of equation has the form x squared minus some number d times y squared equals 1, where that number d is some fixed natural number that's bigger than 1. But by the way, it's also square free, but let's not worry about that. Diophantine equations of this form are actually called Pell equations, named after the 17th century British mathematician John Pell. Unfortunately, Pell really did not study these equations at all. Gauss mistakenly attributed the study of these equations to Pell, and the name stuck. In fact, we now know that these equations have been studied for thousands of years. But it's kind of fun. If a very famous mathematician calls them Pell equations, we all call them Pell equations. Well, our challenge is to determine how many natural number solutions does a Pell equation possess. Well, remarkably, we can always find a natural number solution to any Pell equation, and we'll actually see how we can find one way at the end of the course in lecture 23. For now, we'll just assume that we have this one solution in hand. And as we're about to see, that one known solution can be used to generate yet another solution. Fermat developed a method for showing that a certain Diophantine equation has infinitely many natural number solutions. His clever procedure is now known as Fermat's method of ascent. And his idea is to first find one natural number solution to a given equation, and then use that very solution to generate another larger solution. If he repeats this exact procedure with the new solution, then he produces another still larger solution. And in this manner, Fermat's building an endless tower of ever-growing natural number solutions. Hence the name method of ascent. We're building an ascent. Well, to illustrate Fermat's method of ascent, let's return to our Pell equation, x squared minus 2 times y squared equals 1. Well, it's not very difficult to actually find one solution. In particular, let's notice that x equals 3 and y equals 2 are in fact natural numbers that satisfy the equation. 3 squared is 9, and if we subtract off 2 times 2 squared, then we would be subtracting off 8, and we see 9 minus 8 equals 1. So it's a solution. Well, since this is the first solution that we found, let's call these values x1, that will be 3, and y1, that will be 2. So that's our first solution. Well, we'll now use this solution to recursively define future solutions. For any natural number n, we define the numbers x n plus 1, which means the n plus first solution, to be equal to 3 times the previous x, or 3 times xn, plus 4 times the previous y, 4 times yn. And we define the n plus first y solution, which I'll write as yn plus 1, as 2 times the previous x solution, or 2 times xn, plus 3 times the previous y solution, or 3 times yn. Well, notice that these are indeed recursive formulas. In fact, they are in some sense a pair of recurrent sequences, which we studied earlier in the course. So, for example, x2 would equal 3 times 3 plus 4 times 2, which is 9 plus 8, which equals 17. And y2 would equal 2 times 3 plus 3 times 2, which equals 6 plus 6, or 12. And if we substitute these new values in to the left-hand side of our equation, we'd see 17 squared minus 2 times 12 squared, which equals 289 minus 2 times 144, which is 289 minus 288, which equals 1. It's like magic. In other words, we just found another larger solution to our Pell equation. Let's now prove that these recursive formulas always generate a new solution from an old. In particular, if we assume that xn and yn is a particular solution to x squared minus 2y squared equals 1, in other words, xn squared minus 2 times yn squared equals 1, then let's see what happens if we compute xn plus 1 squared minus 2 times yn plus 1 squared and see if we get 1. Well, if we plug in the definition for these values, xn plus 1, yn plus 1, as we define them recursively, then we'd see the quantity 3 times xn plus 4yn all squared minus 2 times 2xn plus 3yn all squared. Well, now we have to square all those things out, and it's going to get a little bit messy, so just relax and I'll do it for us. But let's just take in all the fun algebra. We'd actually see, after we square it all out, 9 times xn squared plus 24 times xn times yn plus 16yn squared minus 8 times xn squared minus 24 times x and yn minus 18yn squared. And isn't it marvelous to see all those symbols running around, especially since we're not going to be tested on it? Well, notice that we have a 24x and yn, and then I'm subtracting 24x and yn, so they actually cancel out. They add to give 0. And I have a 9xn squared, but then I subtract 8xn squared. That leaves me with just xn squared. And then finally, you'll notice that I have 16yn squared minus 18yn squared, which gives me a net result of negative 2yn squared. And so look what I get. I get xn squared minus 2yn squared. Everything collapses down to just that. But xn and yn are known solutions to that equation, so that has to equal 1. And so therefore, when I plug in xn plus 1 and yn plus 1, I see I get 1 in general. Well, therefore, we conclude that xn plus 1 and yn plus 1 is indeed another larger solution, and hence we have an endless list of natural number solutions, because I can now use the exact same method with this larger solution to build one larger still. Well, this method of ascent can be generalized and applied to any Pell equation. Therefore, we conclude that all such Pell equations have infinitely many natural number solutions. Well, before leaving the Pell equation, I wanted to foreshadow some ideas we'll explore in greater depth in our sojourn into algebraic geometry to come. In this direction, I want us to momentarily consider a curve associated with the Pell equation x squared minus 2y squared equals 1. Well, if we consider all decimal numbers, or in other words, all real numbers, that satisfy this Pell equation, then we could actually plot all those points in the xy coordinate plane. Those points from the graph of the curve actually give rise to the actual graph or picture that we could look at that's associated with this curve. This particular curve is a shape known as a hyperbola, and it even has two perhaps scary-looking asymptotes, which the curve approaches and yet never touches. Let's now place dots at all the points on the plane whose x and y coordinates are each integers. Well, we see a grid-like lattice of points. So asking if there are any natural number solutions to our Pell equation is equivalent to asking if this curve passes through any of these regular lattice points. Well, notice that this curve passes through the lattice point 3, 2, which corresponds to the solution we found, x equals 3, y equals 2. Well, it's not obvious that this gently curving graph passes through infinitely many of these integer lattice points, but we've just shown algebraically through Fermat's method of ascent that the curve, in fact, does. And thus we see a visualization of this algebraic fact. And we can see this great connection between the geometry and the algebra, which we'll exploit later. Well, as we mentioned in Lecture 9, David Hilbert, in his famous Paris address in the year 1900, stated 23 open questions that he believed were the most significant mathematical challenges at the dawn of the 20th century. Hilbert's 10th question can be phrased as, given a Diophantine equation with any number of unknowns having integer coefficients, devise a process that will determine in a finite number of operations whether the equation is solvable in integers. In other words, Hilbert asked if there exists an algorithm for determining whether or not arbitrary Diophantine equations have integer solutions. Well, mathematicians studied this most challenging question for 70 years. Finally, in 1970, the Russian mathematician Yuri Matyasevich gave a complete answer. No, there cannot exist a general algorithm that will always determine, in a finite number of steps, if an arbitrary Diophantine equation has an integer solution. No such algorithm exists. Well, his deep and complicated proof involved constructing a system of 10 simultaneous equations. But one aspect of his incredible argument is not so foreign to us. Surprisingly, one of the key pieces of his argument involved a delicate and important result involving, of all things, Fibonacci numbers and recurrence sequences. So here again, we see the importance of these key ideas developed much earlier in our journey through number. In fact, Hilbert's question connects number theory with very subtle issues from logic. Actually, many questions that we've already considered, including the Goldbach conjecture involving primes and the Riemann hypothesis, have been shown to be logically equivalent to asking if there are integer solutions to certain complicated systems of Diophantine equations. If a Diophantine equation, or a system rather, of Diophantine equations has no solutions, then the answer to its associated open question would be yes. Roughly speaking, every mathematical question involving arithmetic can be converted into a question involving Diophantine equations. So, equations that resemble the kind that we're studying in our algebra classes from years ago can be expressed to show questions in mathematics that actually transcend number theory. In other words, every difficult question in mathematics or easy question in mathematics involving arithmetic can be converted to a Diophantine equation in which we're looking for integer solutions. These Diophantine equations are foundational in our study of mathematics and our understanding of the world.